Hi all, today we are going to derive a solution for one-dimensional wave equation using method of separation of variable. Consider the wave equation. So in order to derive a solution for one-dimensional wave equation, we consider the boundary condition y equal to 0 when x equal to 0 and y equal to 0 when x equal to L. That means we are assuming that the end temperature of the rod is 0. And also the initial condition y equal to f of x when t equal to 0, that is the initial temperature of the rod is y equal to f of x, and the rate of change of temperature is 0 when t equal to 0, that is the initial rate of change of temperature is 0, that is the initial condition. Now applying our method of separation of variable, let y equal to xt be the solution, where x is a function of x alone and t is a function of small t alone. Then we have dou square y by dou t square equal to capital X t double dash and dou square y by dou x square equal to x double dash t. Substituting in given equation, we get x t double dash equal to c square into x double dash t. Separating the variables, we get x double dash by x equal to 1 by c square into t double dash by t. Now the left hand side of the function is a function of x alone, and right hand side we have the variable t alone. That means a function of x alone is equal to a function of t alone, which is possible only if both sides equal to a constant. So let it be k. So we have two equations, x double dash minus kx equal to 0 and t double dash minus k c square t equal to 0. These are second order homogeneous differential equation with a constant coefficient. To solve a second order homogeneous differential equation with a constant coefficient, we have to write the corresponding auxiliary equation. So here the auxiliary equations are m square minus k equal to 0 and m square minus k c square equal to 0. Writing auxiliary equations are quite simple. You have to replace the derivative by corresponding power of m. So x double dash becomes m square. M square minus k equal to 0 and m square minus k c square equal to 0. Solving these equations, choosing k as a positive number, 0 and negative, we can solve this equation by assuming different possible values for k. Case 1, if you take k as a positive number, that is always positive, how can we represent k always positive? Put k equal to p square. We know that square of a number is always positive. So put k equal to p square. What we get? The first equation become m square minus p square equal to 0 and second equation become m square minus p square c square equal to 0. Solving this equation, we get m equal to plus or minus p and m equal to plus or minus pc. So the complementary function is capital X equal to c1 e raised to px plus c2 e raised to minus px and capital T equal to c3 e raised to pct plus c4 e raised to minus pct. If you have any doubt regarding how to form this capital X and capital T, please refer the portion second order homogeneous differential equation with a constant coefficient. Case 2, when k is negative, say k equal to minus p square. We know that p square is always positive. So in order to take k negative, take k equal to minus p square. That is m square minus p square equal to 0 and m square minus p square c square equal to 0. That means m square plus p square equal to 0 and m square plus p square c square equal to 0. That is m equal to plus or minus pi and m equal to plus or minus pci. The corresponding complementary functions are x equal to c1 cos px plus c2 sin px and t equal to c3 cos pct plus c4 sin pct. Case 3. When k is 0. When k is 0, our equation become m square equal to 0 and m square equal to 0. That means we have two roots 0 and 0 for both the equation. So x equal to c1 e raised to 0x plus c2 x e raised to 0x and t equal to c3 e raised to 0t plus c4 t e raised to 0t. So we have three different cases, and in each of the cases we have both x and t. So taking our solution as x into t, we get three different solutions for one-dimensional wave equation. All these three equations are mathematically feasible, but since we are dealing with a problem on vibrations of string, it is a periodic function of x and t. Therefore, the physical solution of one-dimensional wave equation must involve trigonometric functions like sine or cosine. Accordingly, we will take our solution as y equal to xt, which is y equal to c1 cos px plus c2 sin px into c3 cos pct plus c4 sin pct, which is the physically possible solution of one-dimensional wave equation. Note that solution corresponding to all the three cases are valid mathematically, but this is the only possible solution for the one-dimensional wave equation which is physically possible and which corresponds to the negative value of k. Now let us apply the boundary condition. Our first condition is y equal to 0 when x equal to 0. Substituting x equal to 0 and y equal to 0, we get 0 equal to c1 into c3 cos pct plus c4 sin pct equal to 0. That means a product equal to 0. It's clear that the term inside bracket is not always 0. So the only possibility is c1 equal to 0. So substituting c1 equal to 0, we get our new solution as y equal to c2 sin px into c3 cos pct plus c4 sin pct. That's our equation number 3. Now take the second boundary condition, y equal to 0 when x equal to L. Put x equal to L and y equal to 0, we get 0 equal to c2 sin pl, c3 cos pct plus c4 sin pct. Again we have a product of three different terms is 0. It's quite clear that the term inside bracket is not always 0. And if we take C2 equal to 0, the entire solution become collapses to 0. We are not looking for an obvious 0 solution. We are looking for a non-zero solution. So C2 not equal to 0. So the only possibility is sin PL equal to 0. That means sin PL equal to 0 means sin PL equal to sin n pi for some n equal to 1, 2, 3. That is PL equal to n pi and P equal to n pi by L for n equal to 1, 2, 3, etc. Substituting this in our equation number 3, we get y equal to c2 sin px plus c3 cos pct plus c4 sin pct. That's our equation number 3. Substituting p equal to n pi by L, we get y equal to c2 sin n pi x by L, c3 cos n pi ct by L plus c4 sin n pi ct by L. Taking c2 to the inside and replacing c2 c3 by an and c2 c4 by bn, we get y equal to sin n pi x by L, an cos n pi ct by L plus bn sin n pi ct by L. This solution is valid for n equal to 1, 2, 3, etc. And we know that the superposition of solution. That means if we take the sum of different solution, we again get a solution for a differential equation. That is known as the superposition principle of solution of differential equation. So taking that, if we take all the sum of the solution corresponding to n equal to 1 to infinity, we get our new solution as y equal to sigma n from 1 to infinity a n cos n pi ct by L plus b n sin n pi ct by L into sin n pi x by L. Now applying the first initial condition, y equal to f of x when t equal to 0. Put t equal to 0 and y equal to f of x. What we get, f of x equal to sigma n from 1 to infinity a n sin n pi x by L, which is nothing but the Fourier sine series of the function f of x. That is, therefore we have the equation for a n is 2 by L integral 0 to L f of x into sin n pi x by L dx, equation number 4. Now apply the second initial condition, that is the derivative of y is 0 when t equal to 0. So in order to apply that, we have to differentiate our solution with respect to t. So differentiating the function with respect to t, we get dou y by dou t equal to, note that you have to differentiate the function with respect to t. So what will happen, a n into dou by dou t of cos n pi ct by L plus b n into dou by dou t of sin n pi ct by L into sin n pi x by L. So you get dou y by dou t equal to sigma n running from 1 to infinity a n into derivative of cos is minus sin n pi ct by L into the derivative of angle is n pi c by L plus bn into n pi c by L cos n pi ct by L sin n pi x by L. Now we have dou y by dou t equal to 0 when t equal to 0. Substituting this, we get 0 equal to sigma n running from 1 to infinity a n minus n pi by c L sin 0 plus b n n pi c by L cos 0 sin n pi x by L. That is 0 equal to sigma n from 1 to infinity b n n pi c by L sin n pi x by L, which is possible only if the left side is 0, right hand side is also must be 0, and is possible only when bn equal to 0 for all values of n. Right now we have equation for both an and bn. Now substituting bn equal to 0 in our equation, we get y equal to n running from 1 to infinity sigma n running from 1 to infinity a n cos n pi ct by L sin n pi x by L, where a n equal to 2 by L integral 0 to L f of x into sin n pi x by L dx, which is the solution of one-dimensional heat transfer equation.